Hello, good day, and welcome to Yebo Tutor. Are you right? How was your past week? I hope we managed to work and to come up with some shapes like we discussed last time. So, did we manage to finish off those questions as we discussed? Did we manage to work out the rest of the questions? Let's hope so. So we are back at it again, and today we want to look at some shapes and some bond energy. Some shapes and some bond energy. Right, in case you are here and you'd like to join the discussion, feel free to just comment and tell us what questions you would like us to work on. We promised that we'll be working out questions according to the papers, right? So we have papers since 2015 up to 2018, and we work out each set of questions that are within a certain topic. So it's very important that you make sure that you revise so that we are comfortable at the topic. You want to look at all angles of the topic if possible. Right, so that's our task for today. So let us know if you are watching, and also drop in your question on the chat. Drop in your question on the chat so that we can get cracking. Okay, so let's start now with let's check the questions that we went through last week, and then we'll see the ones that are left. Right, last week, this one is the grade 11. Let's just see what we worked out. Okay, so we worked out this one. Still remember it? Did you manage to read about electronegativity? Did you manage to read about electronegativity? I hope you still remember. So we picked up this question from what we were working on. Right, then we also looked at bond length. And you should be able to tell that now if we are discussing bond length. Then we're looking at the distance between the two orbitals. There is something that I remember. From one of the gadgets that we had. There's one of the gadgets that we had, which we used to explain the bond length. There's a bond length calculation, right? There's a bond length calculation that is based on another question. So I'd like to put these things together. So this was the question, right? This was the question, and it has to do with what? It has to do with the bond length. And we're looking at the average distance. And remember, this is an average distance. Average distance between the nuclei. Right. So let's see the question that had that bond length. It was now being plotted as a function. So I think it may have been the 2017 paper. We actually answered some of these questions. Yes, there we go. Okay, so we answered the first question, which had to do with the bond with the highest polarity. And we said we look at polarity in terms of the difference in the electronegativity, the difference between the electronegativities. And we said you can even use this data sheet and just scroll down to the periodic table. Look at the electronegativities. So obviously, for this question, let's come back to it. Hydrogen, carbon. What is the difference in electronegativities? So we are just trying to see how we got to that answer, right? So that would be the 2017 question paper. So that would be question 1.1. We can actually just put it as a 2017 question. So that's 2017 question 1.1. So we have, so let's look at the molecule, right? So let's look at the combination, and then we identify the difference in electronegativities. So let's have the species, and then electronegativity, and then the difference. So I'm trying to tabulate this. If you have a calculation that you can actually use, you can just share with us. So we've got a species, for example, the first one we have H, and then we have carbon. So that would be the first set there. So we want to find the electronegativity of the species. So let's just calculate electronegativity. Let's call it En. Let's call it En. For hydrogen, we come to our data sheet. Hydrogen electronegativity, the value is here. So remember looking at this value here. So that's it, 2.1. Carbon, we come to carbon, and we are taking a 2.5. So what is the difference? What is the difference? Delta electronegativity, what is the difference in electronegativities? In this case, it's 2.1 subtracted from 2.5, isn't it? So the difference is 0.4. Let's go to the next set, B. Let's go to the next set, B. What is in B? On B, we have HCl. We have HCl, right? And H is still a 2.1 in terms of electronegativity. And then what is the electronegativity of chlorine? We come up to chlorine. Where is chlorine? There we are. It's a 3.0. 3.0. So our difference is 3.0 subtract 2.1. That would be a 0.9. C. C is HO. HO. And we're still continuing up to D. H is still a 2.1. How about oxygen? How about oxygen? Oxygen is a 3.5. So our difference, 3.5 minus 2.1. What are you getting? Then the last one, D. The last one is HN. HN. We still have a 2.1 there, and then we have a 3.5. Sorry, we need to look for nitrogen now. We need to look for nitrogen, and it's a 3.0. So do you see, can you see a trend already? Can you see a trend already? There's already a trend, but it will fail somewhere here, right? It will fail somewhere here. So already, as you can see, our most electronegative in this case is oxygen. The fact that these are exactly the same means our indicator in this question is simply the what? The other species. So we now have our 3.5 as the most electronegative atom. So this means our C is going to be the highest polarized set. The highest polarized set. Any questions on that? That was the first question. Actually, that was the first question, which had to do with question number 1.1. Right? So we have our solution, which is HO. So the second question had to do with solid iodine, which sublimes easily, right? Solid iodine, it sublimes easily. So it easily changes state into the gas phase. The intermolecular forces present in iodine are what? The intermolecular forces which are present, which are forming this, which are making it very, very easy for it to sublime. Which ones are these? The intermolecular forces that are making it very easy for it to sublime. Which ones are these? So we've got London forces. We said the London forces are associated with what? Remember last week? Hydrogen bonds. Are they ion dipole? Are they dipole-dipole forces? So I think if you still recall, with this one, we would have our solid iodine because it has London forces. Now, this one is the one which I wanted to make use of for this calculation, which has to do with bond length. So this question has to do with bond length, and what we just wanted to use, right? What we wanted to use is this graph. So where do we get this graph? We can actually see it from our tool. We can actually see it from our tool. Where is that tool? Still remember this tool, right? Where it's some bonding of two atoms, atomic interaction, right? Yes, there we go. So that was the atomic interaction tool. So the whole idea with this atomic interaction tool is that it will show us a plot of potential energy versus distance between atoms. So it's showing us potential energy versus distance. Let me just write this question in context so that we know what we are discussing. So this is now the this is still 2017, right? Question 1.2, 1.3. So this question has to do with bond length. So it has to do with bond length. Right, so this part in the 2018 question, it was asking us the bond length is the average distance between what? So we had all these options: orbitals, electrons, nuclei, and molecules. And we agreed that it's in between two nuclei. So in this tool now, we are making use of those two nuclei. So we have the first nucleus, right? The first nucleus of the first atom, right? So we have some examples that are provided here, right? We might be able to see maybe some forces, but that can be discussed later. So we have some elements: neon, argon, oxygen, neon and argon, neon and oxygen, argon and oxygen. So these are just examples that are showing us what's taking place. So if you have, for example, an oxygen molecule, this is how this program would show. So let me just see. Okay, we can zoom in and out of the graph. And then if you choose a neon argon molecule, that's what you would see. An argon gas molecule, a neon gas molecule, right? So that is what we are seeing here. So in the 2017 paper, the 2018 paper has the question, right? So which was focusing on the internuclear distances. So we say that is the bond length. So we're happy with that. Now, this question on 1.3, right? It says the graph below shows how the potential energy varies with the distance between the nuclei of two nitrogen atoms. So how the potential energy varies. So this is the variation of the potential energy. This is the variation of the potential energy. I'll just write it as PE between the nuclei of two nitrogen atoms when a double bond between the nitrogen atoms is formed. Right. So let's also maybe just build that, right? Let's also build that and see how this double bond is formed. How did we say we build the NN, or how do we build the atom or the molecule? All we need to do is to open our data sheet and scroll straight to our nitrogen. Our nitrogen, if they are individual nitrogen atoms, we know we have 7 electrons in the outermost shell. Where can we pick these? These are neutral, isn't it? These are neutral. So if you wanted to build a neutral nitrogen atom, you can come to build an atom. This is a molecule. So we'll come here. I think I'm looking for build. Okay, we'll also use this, but I want to just find where we can build an atom. We want to just build an atom. So we want the Lewis structure, right? We want the Lewis structure. So this is what we want to build, right? We want the Lewis structure. Right, so what am I looking for? I'm just looking for an atom, and we want to make it a neutral atom. To make it a neutral atom. Right, so we've got, okay, so it's the very last tool there. So this is free, right? This is free. You can jump online and access this tool. It can help you to understand some things which may be a little bit difficult straight from a textbook, right? So it can bridge the gap there because you can actually interact with the tool and play around with it. So our Lewis structure is our first target. So according to the Lewis structure, how do we build this? According to the Lewis structure, how do we build this? So we just want an atom. We will see the element here. We can then see the net charge. This is the mass number. According to the periodic table, we have 14 nuclides. According to the periodic table, we have 14 nuclides in this atom. So it has what? It has 14 nuclides, which means the number of protons plus the number of neutrons should become 14. So we can take our protons, and we've got 1, and we've got 2, we've got 3, we've got 4, we've got 5, we've got 6, and then we've got, can you see the name of the element immediately pops up because the proton number is the identifier. Then we can put our neutrons. So we're putting in 7 neutrons. Where are we getting it? Because it's 14 on the periodic table. So since we've already put 7 protons, then we're putting 7 neutrons. But can you see the status of this? This is still what is called a what? An ion. So let's get to 7, right? The difference between them is shown in this corner here, right? So you can actually tell if we're almost there. 6 and then 7. We have equal numbers now. So we're at what? A nitrogen. The nucleus is okay. So we're happy. Now let's put in the electrons. 7 electrons in the outermost shell. So what is our anticipation? We anticipate that our nucleus, our Lewis structure, looks something like this. So it's supposed to have 7 electrons in the outermost shell. So let's pair them. First 2, they are now a pair. Second 2, they are now a pair. Now we have 6. And then we have the 7th. That is what we expect to have. The same should apply on the right hand side. We should have 1, 2, 3, 4, 5, 6. Right, 7. So 2 should enter straight into the innermost shell, isn't it? 2 should enter straight into the innermost shell. So if 2 are into the inner shell, then how many do we have on the outside? We remain with 5. So on the outside, we should remain with 5. So which means we can actually plot only up to there. So let me maybe just put it here so that we can see how they will connect. So let's put in the 7 electrons. So we are putting in the 7 electrons now. This is the first. So the moment we drop it into the atom, it falls into the innermost shell. So it's a requirement that we fill in the innermost shell first. So that's our first electron. Let's jump on to the second. The second electron is into the innermost shell again. Note that repulsion is making these electrons to be as far apart as possible so that the system is stable. Okay, so we can also have an indication of whether or not this nucleus is stable. If we were to take out one of the nuclides, then it becomes unstable, right? So we can see that it's dancing around. And then if we put in and they are enough now, then it is stable, right? So it's a very, very, very useful tool. So let's fill in. We have already put in 2 electrons, but this is still an ion, right? This is still an ion. So at the outermost shell now, at the outermost shell, it means that the remainder will fill in the outermost shell. So let's fill in 1, 2. Look at our charge. Look at our charge. Our charge was mostly positive, isn't it? Because we had, we did not have these electrons. So look at our charge. Our charge, if we remove the electrons, look at it. It's very, very positive, right? So we're now putting in our electrons. So these are the 5 at the outermost shell. 1, 2, 3. Look at our charge. 4. Our charge meter is actually getting to 0. Then 5. So we now have a neutral nitrogen atom. So with 5 electrons in the outermost shell, right? With 5 electrons in the outermost shell, then this bonding, the bonding requirements. What are the bonding requirements? The bonding requirements will show that we will end up having a state that has been shown here, where they say it's becoming a double bond. So where is it? There we have it. So the graph is showing how the potential energy varies with distance between the nuclei of 2 nitrogen atoms when a double bond between the nitrogen atoms is formed. When a double bond between the nitrogen atoms is formed. So if we have this only, we will have a single bond, isn't it? We'll have a single bond. The moment we bring this electron and that electron to participate in bonding, we have a second bond, right? We have a second bond. So now we have a double bond. Now we have a double bond. So if we have a double bond, let's also see how we can build such a molecule, right? So according to what we have here, we are looking for 2 nitrogens, isn't it? Molecular nitrogen. This is what we're looking for. So I'll just try to see if we can find some nitrogen. Do we have some nitrogen? Yes, we have some nitrogen here. So this is what we're building. So that's our first nitrogen, and that's our second nitrogen atom. Now let's make a nitrogen molecule. So we'll just put them together. So now we have a nitrogen molecule. So if we are to make it a little bit, okay, they're separated. If we are to make it a little bit more pictorial, you can just click there so that you can see the nitrogen molecule. And there's our bonding structure. So ideally, we would actually need to have this, these 2 coming on to participate in the bond. Can you see that it's actually 3, right? It's actually 3 electrons that are bonding. But in this case, we have a case where we have 2. So that's what has been given in the question. So we have our nitrogen. It is a double bond, and we're happy. And according to the question now, this is the potential energy. This is the potential energy when we have these 2 nitrogen atoms forming a bond. So the question had to do with something else. It says, choose from the table the bond length for the bond length and bond energy for n double bond. So obviously, if you'd want the stable set, isn't it here? R, or the distance, is still increasing, right? This is the distance between the nuclei, right? When the distance is very, very close, almost nearer to 0, the potential energy is way too high. Potential energy becomes 0, in this case for nitrogen, at 120 picometers, right? Then that potential energy changes. It was now in the negative, and then it is now approaching 0 once again. So in this second cycle, then it means that we are getting our values from here. We did this question, so I'm sure you know what's happening. So we just want to relate it to what's happening in our tool this time. So let's just try and identify. We just wanted to see, I think we don't have a nitrogen molecule here. We don't have a nitrogen molecule, which is not a problem. But we do have we do have that tool that we had here. Yes, we do have the tool that we had here, right? According to what we have here, we do not have nitrogen, right? We do not have nitrogen. So I'll just choose oxygen, oxygen, so that we can see if what's in the graph here actually agrees with the measurement. That's in this tool. So let's just see the value there. Let's just see if we can find the value, right? Let's see if we can find the value. Right, so this is the distance between them. I don't know if I can zoom in. Okay, so this is what is taking place here. I cannot see some values. Let's just see if we can see the forces. Okay, so we're just seeing the forces there. There's attraction and then there's repulsion. So when we are still this is too fast. This is too fast. Maybe let's see if we have another one which can exemplify what's happening here. Right, so as we bring them closer, right? As we bring them closer, there is a point at which we can determine that the attraction is now equating to the repulsion, right? The attraction is now equating to the repulsion. The moment the attraction turns to repulsion, that is where our bond length is, and it is at this knee of the graph. That is why our value for the previous question was taken there. Okay, so any questions on what the meaning of this graph? Basically, we are deducing the meaning of this graph from this question. We are deducing the meaning of this graph from this question. So in this whole part of the graph, the nuclei are separate, but they are attracting each other. They are separate. As you can see from there, if we zoom in, when we are on this part of the graph, on this side of the graph, when the nuclei are very far, then the potential energy between them is zero, right? The potential energy between them is zero. As they are brought close to each other, so let's just have that move in, right? They are getting close to each other. Can you see that there's some attraction? A point is reached when the positive nuclides, the positively charged nuclides, begin to repel. So that repulsion is what we see on the other side. That is the repulsion there. So that repulsion takes place in this part of the graph. And if we keep bringing them very close, the repulsion is infinite. So in other words, you cannot actually put them together. Okay, so that was our Lewis structure. And then what we had was the graph. So this is just a graph of the potential energy as a function of distance between the nuclides. Distance between the nuclei. Right. I think this one covers the meaning of this graph. We just had some values. Let's just see if we can find that for oxygen, because we already have something here. So how would we plot this graph? The values are shown here, right? The values are shown. So you would see that the knee is far below. Let's just see for argon, very close to zero, but we do not have some numbers here, so we may as well not really worry ourselves, because we won't find an actual calculation. Right, so basically that is the use of this graph. Right, let's jump on to the next paper. We are now on question on the 2016 paper. We are now on 2016 paper. Right, so these are also questions that have to do with bonding. The first question, 1.1, first question, the type of bond formed between a hydrogen ion and water is called, what is it called? The type of bond between a hydrogen ion. Question 1.1. So the type of bond between a hydrogen ion and water. How can you figure this out? How can you figure this out? Remember, we categorized species last week, and we said the type of bond between two species is determined by the type of the species as we compare with electronegativities and the difference between the electronegativities of the constituent elements within those that element of those the participants of this compound. So for example, in our previous question, we even looked at the difference in electronegativities, isn't it? So we now want to find what's happening with hydrogen. First of all, let's look at the species and their types. Right. Hydrogen is an ion, isn't it? Hydrogen is an ion, H+. How about water? What type of species can we put water in? What type of species can we put water in? Water is, what type of species can we put water in? Is it a weakly polarized? Is it non-polar? Is it strong polarized? What type of species is water? What type of species is water? What type of species is water? Right? So water, we know that it is what? It is a polar molecule. Water, we know that it is a polar molecule. So if it is a polar molecule, right, and it is interacting with an ion, what type of bond is formed between them? What type of bond is formed between them? So let's just draw our water molecule. Let's draw our water molecule. Central atom, we'll start with the central atom. So we put in our oxygen. So let's just have a Lewis diagram. So we've got our central atom, that's our oxygen. Central atom. Oxygen has how many electrons in the outermost shell? You can just jump onto your periodic table, just see that, oh, okay, oxygen is in group what? It's in group 6, right? It's in group 6. So it should have 1, 2, 3, 4, 5, 6 in the outermost shell. Next, it's bonded to hydrogen and it makes a stable molecule. So it is bonded to hydrogen and it makes a stable molecule. So how would these bond? Obviously, hydrogen donates one of its electrons to this bond. The oxygen is highly electronegative, isn't it? So it is the one which tends to pull all the bonding electrons to itself. So in the end, we'll just use 2 of these electrons. So we can even just shift our diagram. We can just change our diagram so that we have something like that. So let's take this other hydrogen and bring it here with its electron. Oxygen, we said it has 6 electrons in the outermost shell. So we can put this electron here. So now we have 6 for oxygen and we're happy. So what I'll do is to just take this very close, right? Take this very close because this is what oxygen does. It is highly electronegative. Electronegativity is 3.5. So remember our previous question. So this is the HO bond. This is the HO bond. So all the electrons are closer to the oxygen. So the oxygen ends up with a delta negative. Now this is our lone pair, isn't it? This is our lone pair. Now, the next thing is, so let me just put delta plus here, delta plus here. The next thing is that in this setup, rather let me move my diagram so that it comes into the field of the picture. Good. So in this setup, the next thing that we have is we are given now a hydrogen ion. We are given a hydrogen ion. So we have an ion. We have an ion, and we have this polarized molecule. This is the polarity. These are the poles, right? The electric poles, where we have a positive and a negative. So now the question is, when this hydrogen comes into the picture, what kind of bond is it likely to form? It has no electrons in the outermost shell because it's a hydrogen ion. So first of all, we are looking at an ion that is interacting with a polar molecule. First of all, we are looking at an ion that is interacting with a polar molecule. What kind of bond are they going to make? What kind of bond are they going to make? What kind of bond are they going to make? So here, do you already see that there's the ion dipole interaction, right? There's already some ion dipole forces that are what? That are pulling this hydrogen. So we have some ion dipole forces that will pull this hydrogen into our setup. Okay, so we have ion dipole forces. They pulled the hydrogen to the dipole. Now that they have been brought close to each other by the ion dipole forces, the next thing or the next question is, so then what kind of a bond is likely to take place? So if you were to bring this hydrogen into the picture, what are you having now? So you have a hydrogen. It is it does not have an electron. If it does not have an electron and you're supposed to form a bond, then this bond is supposed to have how many electrons? How many electrons? We need 2 electrons, isn't it? So we take this hydrogen, there's nothing in the outermost shell, and the only electrons for bonding, the same way we had 2 electrons here to form the HO bond, the same way we had 2 electrons here to form the HO bond, we now have 2 electrons. We now have 2 electrons to form another HO bond. So there are some things to think about. Number one, this is the interaction is an ion dipole interaction. Number two, the forces that pull the hydrogen ion, or the force that pulls the hydrogen ion, is the ion dipole force. Then when the hydrogen has been pulled, then the type of bond that is formed, the bond is formed by any of the two lone pairs. Any of the 2 lone pairs. These are our lone pairs. So this is lone pair number 1. This is lone pair number 2. Lone pair number 2. So as long as we now have our 2 electrons participating, we're happy. Then the hydrogen is now what? Is now part of this. And what have we formed? We have now formed the H3O species. We have now formed the H3O species. So in this case, then it means the type of bond that is formed in this question, the type of bond, you can now deduce it. So which one is it? Type of bond between H plus and H2O. Type of bond between H plus and H2O. Which one is it? So you can now select. Is it a hydrogen bond? Is it a dative covalent bond? Is it an ionic bond? Is it a covalent bond? Only just normal covalent bond. We can even distinguish them, right? We can even distinguish them. This is a covalent, isn't it? Sharing of electrons. Sharing of electrons. This is what is taking place here. So that is the covalent bond. How about this one? What type of bond is it? How about this one? What type of bond is it? What do you call it? This new bond that is available here. What do you call it? Where you have, this is our water. Where is the water? Where is the water molecule? Yes, there is our water molecule, right? So this is our water molecule, and these are the lone pairs, right? These are the lone pairs. Those are the ones that we identified when we drew the Lewis structure. We had one lone pair, we had the second lone pair. So these are the two lone pairs. They make these nice ears, right? And then this is the oxygen in the center, obviously, and then we've got our two hydrogens. So that is what we are seeing in this molecular geometry. So the question is, what is the name of this type of bond? So this is a bond that is formed when there is an interaction between one element that has a lone pair and another element that has a vacant outermost shell. So this is just an interaction between those two. So what we actually have seen there is basically a dative covalent bond. So this is the dative covalent bond. Covalent bond. Dative covalent. Okay, so let's hope that exercise is you can easily remember it, right? Let's hope that you can easily remember that exercise, which basically brings us to the end of the first question for the 2016 paper. Right, so it's actually very, very important for you to build your argument or build your answer logically. Build your answer logically. So we have seen that this was an interaction. We've identified the type of force, and then the bond that has been formed is because of that pair. Okay, so I hope that was helpful for you. The second question, the shape of the molecule in which the central atom is surrounded by two lone pairs and two bond pairs. The central atom is surrounded by two lone pairs and two bonding pairs. Do you remember what we drew? The water molecule that we used in this question is exactly what we are seeing here. So this is the shape of a molecule in which the central atom is surrounded by two lone pairs, and then it has two bonding pairs. So in our case, we actually had it. We actually have, maybe let's just write it as 2016. This is question 1.2. So for let's just use water molecule. For the water molecule. So what we have is the central atom. So this is our central atom. It has how many lone pairs? Two lone pairs. So you can just draw the lone pairs here. Then it has how many bonding pairs? It has two bonding pairs. So there we have it. This is a bonding pair with one of the hydrogens. This is a bonding pair with one of the other hydrogens. So its own is this one. So this is our bonding pair. bonding pair. Then this is our lone pair. Lone pair. And then we said bonding pairs. Bonding pair. So we have two bonding pairs and two lone pairs. And that's what we have in this question. So their question has to do with us trying to identify the shape of this molecule. Trying to identify the shape of this molecule. So the first one, the first option is a linear. The first option is a linear. Remember, there is a table already. Remember, there's a table already that you can find in your textbooks that directs you towards finding a molecular shape. So there is a table that you can actually use to find molecular shapes based on the number of lone pairs, number of bonding pairs. Right. So here we have the first one, linear. So let's just look at how a linear molecule looks like. Let's look at a linear molecule. Let me also see if there is an option for us to select our lone pairs and bonding pairs. Let's see if there is an option for us to select our lone pairs and bonding pairs. Our lone pairs and bonding pairs. Right. Here, can we make water here? Yes, we can make water. So let's just see how it will look like. That's our hydrogen, that's our second hydrogen, so that's our water molecule. And if we look at the bonds, right? If we look at the bonds, we have these two bonds, right? We have these two bonds. So these are our bonding pairs. The lone pairs are not easy for us to see, right? In this animation. So what are we looking for? We are looking for the molecule shape. Yes, we are looking for the molecule shape. So we are looking for the geometry, right? So this one will actually indicate a geometry so that we can tell what they mean by linear and so forth. So this is an example of a molecule which is a linear molecule. The linear molecule, it has two of the species, right? Two of the species are equidistant from the central atom. And they are oriented all along the same axis. So this is the same axis. Same axis. You see, even if you look at it from here, right, you can see that this is the same axis. You look at it from that side, it's the axis from the other side, and so on and so forth. So this is a linear molecule. Right? I just want to see if we can model, if we can create the model. Right? Because here we don't have a way of selecting the species. So which of these have the properties that we're looking for? Which of these elements have the properties that we're looking for? That way we can now relate with what we have, right? We can relate with what we have. So let's take an example. BeCl2, we already have it here, right? With two chlorides, right? So we already have it here. It's a linear molecule, so we're done. So we need to now go and see how BF3 will look like. So for BF3, let's put the Lewis structure, right? Let's put the Lewis structure. For the boron, where can we get the periodic table? Here, boron is group 3. Boron is group 3. So let's now have our group 3. 1, 2, and then we can put, in fact, this is our central atom, so we may as well distribute these electrons. Let's distribute these electrons because they'll bond with one fluoride. So 1 electron for each of the borons, for the boron. Then the fluorides, we say there are 3 of them. 1, 2, 3. Right, let's just move this away. So fluorine, group 7, so 7 electrons in the outermost shell. So we're going to take this as 1. And then we'll have, we said 7, so that's our 3 now, that's our 5 now, that's our 7, right? So the same applies. So we're just filling in the blanks. We're just filling in the blanks. That's our bond. Let's fill in the blanks. We are going to have a problem here because we do not have enough for this boron. So we're likely to have one of them forming another type of bond. So that's 6, and then we have 7. So we've got a bond there, and we've got a bond there, and we've got a bond there. But our boron is not stable. Boron is not stable. So if we just look at the molecule shape, this is the molecule shape, right? This is the molecule shape, and it's trigonal planar, right? Trigonal planar or planar. So it's on one plane, right? It's on one plane. The central atom is surrounded by how many bonding pairs? So we can say bonding pairs, and how many lone pairs. So these are our pairs. How many bonding pairs? So we have 3 bonding pairs. 1, 2, 3. How many lone pairs? The central atom. We do not have any lone pairs. So it's not looking like our water molecule, which has 2 lone pairs and 2 bonding. 2 bonding. So let's go to the next. Let's go to the next. We have CH4, right? We have CH4. So this is our CH4. Central atom, carbon, obviously. We come onto this part and we're looking for carbon. It's in group 4. It's in group 4. Let's put in the number of electrons in the outermost shell. 1, 2, 3, 4. Let's bring in the hydrogens. We know hydrogens would contribute 1 electron each. The hydrogens would contribute 1 electron each. There goes our hydrogens. So carbon is now stable. We have 8 electrons in its outermost shell, and we have our hydrogens. They are also happy. Within the first shell, we see 2 electrons. So the bond is done. How many bonding pairs? 4 bonding pairs. How many lone pairs? 0 lone pairs. Right? So we again have a situation like this. There is this other tool. I think it had right. So it has lots of these. So I'm just looking for 2 bonding pairs and 2 lone pairs. Let's just see what happens with CH4. Does it have CH4 on this tool? Yes, it has CH4. Good. It has CH4. And it also has BF3. So you might as well see how BF3 looks like. So this is BF3. It only has what? Bonding pairs. It only has bonding pairs. Remember, with this part of the tool, you can actually see the lone pairs as well. Right? So here we can see only the bonding pairs. Then for CH4, we're already done with it. We said we've got 4 bonding pairs. We'll see it here. We just have 4 bonding pairs. We do not have any lone pairs. There are no lone pairs. So 4 bonding pairs and 0 lone pairs. Which is the next molecule that we had on the other side, which is here. That was CH4. Then we can look at PCl5. PCl5. So we've got phosphorus, pentachloride. Is it? Pentachloride. If it has another name, then it will be different. So this is 5 electrons in the outermost shell. That would be 1, 2, 3, 4, 5. So let's put in the bonding electrons. Let's put in the bonding electrons. It is PCl5, so we should have 5 chlorides. right? 5 chlorides. So if you look at its structure, I think you can already see it drawn here. So we've got 5 bonds, isn't it? So without wasting much time, this will be 5 bonding pairs and 0 lone pairs. And then we can go and see. Let's just see the options that are there. Let's just see the options that are there for this question. Okay, so we already have, okay, we have the category, right? We are using a category, so we are not okay. So obvious, this one would be our guide, right? Just because we can see that water has these, right? We can see that water has these 2 lone pairs and 2 bonding pairs. And what are we getting? This is a bent geometry and it's tetrahedral, isn't it? Bent geometry and it is tetrahedral. But otherwise, I would prefer a case where you can identify it, right? Where you can identify it and you can quickly pick the molecule. So I think this should summarize our discussion today. We've got 2 lone pairs and 2 bonding pairs. So we can finish this off when we meet again, but otherwise, let's just revise. I think we're done with most of these bonding questions. The next would be to then move to ideal gases. So we need to go to ideal gases. So for next week onwards, let's just attempt some questions. Remember, we are going topical. Attempt some questions that are based on ideal gases. Otherwise, this is it. We did a bit of the 2016 paper today. A few questions that are under this topic. 2016 paper. A few questions that are under this topic. Right. So I guess that is our work for today. If there are any questions, we can discuss, or you can send on to the chat group, and then we can see what we can do as far as helping each other is concerned. Right, so there we have it. That's our TAT for today. Let's meet again. Enjoy yourselves and have a pleasant and safe weekend. Thank you very much. Goodbye.